Okay. Okay, so our next speaker is Henry Towsner, and he'll speak about Ultraproducts.
All right. So, of course, I'm not a model theorist or a differential algebraist. I'm a proof theorist, and so my interest in the subject is really in sort of the question of what kind of techniques get used to prove things, and in particular, the way I originally started thinking about differential algebra at all was when my then postdoc, William Simmons, pointed out that ultraproducts had been used to give some proofs in commutative and differential algebra. So I want to mention two examples that will come up again during the talk. So one is a result by Schmidt-Gertsch about bounds on bounds on testing primality of polynomials. So bounds on testing primality of ideals, that's the phrase I'm looking for. So this says if you look at an ideal in the polynomial ring with n variables generated by polynomials of degree d, if you want to know whether this ideal is prime, you only have to test up to products of polynomials whose degree is at most d to the beta. So I should note, being able to test primality of ideals, that's not new, that's well known, there are in general better bounds. The significance of this result is that they're polynomial in D. So that fact, as far as I know, is only known through this proof. So this is sort of an odd proof because he uses an ultraproduct, so he proves that there are polynomial bounds, but not what the degree of the polynomial is. Just there is some bound beta depending on n, but not d, that gives you a bound of this form. Let me come back to that question. That's a complicated and abstract question in the sense that from such a proof it's intrinsically computable. But how about no one has written, the proof does not explicitly write down in any way what beta would be. And another result by Harrison, Traynor, Kleiss, and I don't know, some other guy. Similar but not quite analogous results. You have a system of commuting derivations, so now we're in the setting of differential fields, again over characteristic 0. Now you look at a delta ideal, and you want to know how can you test whether this delta ideal is prime. So checking that you can actually test primality by looking at only bounded degree polynomials is, I think, equivalent to the RIT problem. But what they get is this result that you can keep one of the polynomials of bounded degree and order. So if you check for all the f's and g's where f has bounded order and degree, then you can test whether this ideal is polynomial, and their proof again goes through this ultraproduct construction. So I'm going to refer to this paper a number of times. So HTKM is Harrison, Traynor, Kleiss, and Musa. So the sort of outline of how this proof goes and how ultraproducts come into this is you say, suppose this were false. So that would mean there was a fixed n, the number of variables, m, the number of derivations, and d, the bounds on your the generators of your ideal. So that for every b, you had some example, some ideal in some field, which violates this. So you have an ideal generated by polynomials bounded in degree and order by this bound d, but this ideal must not be prime, but there are no small counterexamples to primality in the relevant sense of this theorem. And the ultraproduct attaches this limit object, which I think most people here have seen in some fashion ultraproducts, but maybe not in detail. But the fundamental idea is it's a sort of universal limiting operation. So you take this sequence of counterexamples and you get this limit, which is a sort of abstract field. And in this abstract field, you get an ideal. It's not exactly generated by these small polynomials. It's internally generated, which is a slightly more complicated notion. But again, it's not prime, and in particular has no counterexamples where f has finite degree and order. This being an ultraproduct, there's a meaningful notion of sort of non-standard or infinite degree and non-standard order that comes into this. But there are no small counterexamples. And then they derive a contradiction. So to be clear, I call this an outline, but of course the entire proof is they derive a contradiction. That's all the work happens. But the point I want to emphasize is the structure, that what you do is you take a sequence of counterexamples, and then you do work in differential algebra in this ultraproduct. And most applications of ultraproducts in commutative and differential algebra, in other fields of mathematics, most applications are at least superficially non-effective proofs of the sort of statements for which you would expect bounds. Right? So Alexei's question, like what is beta? For every n, you should get a beta that's the degree of this polynomial. You might want to know what is that beta. In HTKM, given the number of variables, the number of derivations, and the degree of the polynomials, how far do you have to test? What is this bound be on the degree and order of f, so that you can test whether f times g belongs to this ideal? So these are proofs for which you would naturally ask what the bounds are, and at least on their face, these ultraproduct proofs don't give any kind of explicit calculation. They're this proof by contradiction. And so the questions I was interested in are, so first of all, given these proofs that a bound exists, how do you actually get a concrete bound? And intimately tied into this is the question of, given these proofs that use ultraproducts, how could you not use ultraproducts? How could you take this proof and turn it into a standard proof, and what happens when you do that? And given that at this point we know how to do those first two things, there's sort of the counter question, which is, given that we do in fact know that you can take ultraproduct proofs and turn them into standard proofs, why bother with ultraproducts at all? Why not just do standard proofs? Like what ultraproducts have to give us? All right. So to talk about these first two questions, you have to sort of think like a logician, which is to say you have to think about what proofs are. And so my claim is a proof is a sequence of statements where each statement follows from previous statements. I hope this is not a deeply controversial claim. And I want to note, I mean this in a kind of bifurcated way, in that if you're really thinking like a logician, you might say, like in a undergrad logic class, we sometimes say, a proof is like there's a list of rules, and from A and B you can derive A, and you have to break everything down into rules of first order logic. And so that's sometimes what we mean by this. But I want to emphasize that I mostly mean this in the much less formal way that a journal article is a sequence of statements, and what connects them, what it means to say that one statement follows from previous ones is much looser, and sometimes people say, well, this clearly follows from previous statements, and sometimes it's not so clear when people say that, how it follows. But nonetheless, we can view a journal article as a sequence of lemmas and a sequence of steps in those lemmas, and in some fashion there's a logical connection between these statements.
Assuming it's correct.
Assuming it's correct. Which, and so when I talk about wanting to sort of take ultraproduct proofs and translate them into standard proofs, what I want to mean by that is that we can take the sequence of statements, ideally at the level of a journal article, or the level of a journal article with some careful parsing, and translate them into statements in the ground models, to standard statements. In order to do this, we actually have to, so I don't want to have to break things down into, each step follows from previous steps, the level of detail that first order logic requires. But we do need to figure out what statements are, because statements in journal articles are written in English. And if we want a translation, we can't really hope to translate English in a formal way, as people have tried with, well, surprising success, but not at the level of rigor that we want. So if you ask a logician, like what language you write statements in, I mean, the first thing people are going to say is something like first order logic in a suitable language. So if we're talking about statements about differential rings, like in HTKM, The first thing you might think is, well, maybe the language of differential rings. So we have the language of rings, 0, 1, plus, and times. We have some symbols for the derivations. If you go through a little more carefully, you might want a language for differential polynomial rings where you have some distinguished symbols for the variables x1 through xn, but some first order language of this kind. And this suffices for some purposes. So just for sort of easy example, right? If you want to say a field's characteristic 0, this is not a single first order statement, but it's a conjunction of first order statements. And many things you'd want to say can be expressed in this language. And the fundamental theorem of ultraproducts is about the relationship between first order statements in your original field and first order statements in the ultraproduct. And so this is Walsh's theorem. And what Walsh's theorem says is that if you have a first order, I should really say first order sentence. So a sentence, it's true in the ultraproduct exactly when it's true for most of the ground models. And so you can take first order statements and just pull them up and down as you need them. And on the one hand, this is a very easy translation, right? If you do some work in your ultraproduct and you derive that some first order sentence is true, and you want to know what's going on in the ground models, the answer is that sentence, that same sentence, was true in most of the ground models, usually all but finitely many of the ground models in practice. But also, this is a trivial translation, so nothing interesting is happening here. And what that tells you is when people do work in ultraproducts, they can't be working in first order logic, because it wouldn't do anything for you. So they must be doing something else. And for example, the conclusion, like the last sentence in Harrison, Traynor, Kleist, and Musa, isn't actually a first order statement. So what they conclude with is there is a B, so that if I is an ideal, et cetera, et cetera, et cetera, everything after there is a B is a first order sentence. But there is a B. B is a natural number here. And first order logic doesn't have quantifiers over fixed natural numbers. So, if for the logicians, right, if you try to do this in first order logic, and then when you take the ultraproduct, if you think of this as a first order logic statement, then when you take the ultraproduct, B becomes a non-standard number, and that's not what we want. We really want B to be a natural number. So when we're working with ultraproducts, this is actually very typical, that what we're really working with are statements that mix first order logic with quantifiers over natural numbers, or quantifiers over countable sets that can be encoded by natural numbers. And we want to be careful about which values are genuine natural numbers, right? So here, B is supposed to be an actual natural number. And typically, right, so ultraproducts, proofs that use ultraproducts very frequently involve these statements. They say, well, actually, I want a genuine natural number such that a first order statement holds where this first order statement uses B as a parameter, or if you really try to parse it out, the exact form of the statement depends on B if you try to encode it in first order logic. So you get these statements like this. There is a natural number B so that a first order sentence holds, but what first order sentence it is depends on B. And slightly more generally, you get a lot of statements that say for every natural number A, there is a natural number B, and then a first order sentence holds that depends on A and B. So there's a theorem in non-standard analysis. This is called the transfer theorem. It's not a hard theorem. I mean, people just kind of use it, prove it by hand over and over. So most proofs that use ultraproducts basically go through the transfer theorem at the end. And often they just prove the instance of it they need by hand, because it's not a hard theorem. So this says, suppose the ultraproduct satisfies the statement, for every natural number A, there's a natural number B, so that a first order thing holds. Now, that has to mean that for every natural number A, there's a natural number B, so that in most of the ground models, the statement sigma AB holds. And it almost looks like nothing's happening here. And I want to emphasize that something is happening here, which is that you're getting a uniformity. Right? So the difference between this and Walsh's theorem is there's built into this requirement that B be independent of the particular field you're working in. So truth in an ultraproduct of a statement of this form corresponds to some kind of something happening uniformly in fields in whatever you're talking about. And if you start looking at proofs that use ultraproducts in commutative algebra, in other fields of mathematics where they've come up in functional analysis and combinatorics, first of all, many statements that appear have exactly this form. Like this is a very common form. The conclusion, the things people prove, almost, more than 90% of them have this form. So what people do is they do a bunch of work in the ultraproduct, and then at the end, whatever they were doing in the middle, at the end they get a statement like this, and they use the transfer theorem to say, okay, now I know that something happens uniformly in the structures I was talking about. Something happens uniformly in fields. So, for example, the proof by HTKM uses the fact that this field is flat over this other field. So what do these mean? This is the ultraproduct of the rings. I should say it's a ring. These are both rings, I'm sorry. Right, these are rings. These are polynomial rings over fields. So this is a ring where you take the polynomial rings over K and you take the ultraproduct. Here you take the ultraproduct over K and then you take the polynomial ring over that. This one is sometimes written K-INT, K internal of X, which is sort of a field-specific notation that is not that useful when you're comparing results in different subjects. But the difference here is this first thing includes polynomials of non-standard degree. So it includes these additional sort of infinite degree polynomials. And this one does not. This is an ordinary polynomial ring over an ultraproduct field. And there's this kind of conventional fact that gets used a lot, that the former is flat over the latter. And if you unfold the definition of being flat in terms of solvability of equations of polynomials, and then you apply this idea that truth in an ultraproduct is uniform truth in the original fields, you end up writing down a statement like this. So you say, well, every time you're using flatness in the ultraproduct, the underlying fact that's making that work is this claim that if you can solve a linear system of equations with whose coefficients have bounded degree, then you can find a family of solutions of degree that you can calculate from the degree of the coefficients that gives you all your solutions. So this is sort of, and so whatever you're saying in the ultraproduct, it's got some sort of statement about degrees of solutions in the original thing. And I want to emphasize, this is a statement about just general fields. Right? It says for every B, there's a D, so that in any field, if you look at equations in the polynomial ring over this field, you get solutions, and the bound D for where you need to find your solutions depends only on the degree of the coefficients. As I said, you go through proofs. Basically what happens is you do whatever you do in the ultraproduct. At the end you say, well, for every A, there's a B such that something happens. And that tells me I have a uniform statement about my original structures. What makes life complicated, well, one thing that makes life complicated is that that's not that the intermediate statements in your proof don't have to have that form. So typically you end with a for all exists statement, but in the middle you might use more complicated statements. So conveniently, HTKM has an example. They use noetherianity. And, right, so just to keep to a simple case, I'll talk about noetherianity like this. So for any sequence of ideals, there's a K so that IK, after IK, this increasing sequence of ideals is stabilized. For every M every M greater than or equal to K, IK is equal to I. And logicians will maybe not be happy with me for making this claim, but I'm going to claim this has the form, there is a K so that for all M something happens. you have to get your language right. Like there's something about how you encode the ideals, but maybe you can throw in a set parameter for ideals or something, and this will work out okay. For our purposes, the sort of relevant content is there is a k so that for all m. And it turns out when you have a statement, there is a k for all m in an ultraproduct, the situation gets a little more complicated. So the analog of the transfer theorem is the following. The ultraproduct satisfies there is a natural number A, so that for every natural number B, something happens. So an exists for all statement. And what has to happen in the ground models is you say for every function from natural numbers to natural numbers, there's an A, so that for most of your original structures, for most of the ground fields, you satisfy A comma F, you satisfy A F of A. So in the ultraproduct, you have an A that works for every B. And in the ground models, you just say for every function F, you have an A which works for F of A. So one way to think about this is F of A is like a is like a potential counterexample function. So this comes out of something that's sometimes called the no counterexample interpretation. There is not a counterexample function. Right? So we're trying to persuade you that the original statement is false. So it's not the case that there is an A which works for every B. Well, what they'd have to do is tell you here's a counterexample function. Here's my F, so that for each A, F of A will be a counterexample B. And this is saying that doesn't work even in the ground models. For each supposed counterexample function F, I can at least show you that your counterexample function is wrong. I can find an A so that F of A is not a counterexample. And I can find an A so that A works for F of A. But what makes life complicated is for each F, I find an A that works for most of these fields, but I may not be able to beat every counterexample function simultaneously in just one of these Ks. I have to go to the ultraproduct to actually get a perfect witness that works for everything. So to make this a little more concrete, what does this mean for noetherianity? So true noetherianity would say I can find a K so that K is just the union of this sequence of ideals. K is the top ideal, and from then on the sequence is constant. And what this says is we can look at a local noetherianity. So instead of working from K on forever, I can find big regions. I can find regions from K to F of K where this sequence of ideals has stabilized. But I can't promise that K works forever. So think of F as being some medium-sized function like K cubed or something. So I'm saying I can find an interval so that between K and K cubed, my sequence of ideals doesn't grow. But I can't promise that I found the last one in the sequence of ideals. So if you imagine in practice that the sequence of ideals comes about from looking for new generators. So between ik and im, or ik and ik cubed, I don't find any new generators. So they're a big sequence where I don't find anything new. But then later there might be something new. I can't promise that I have one forever. So this is this local version of noetherianity. So one important feature is if I give you even a sort of reasonably if I give you, say, a sequence of ideals and I tell you about the bounds on their generators, that's not enough information to know how far you have to go to figure out where this sequence of ideals stops growing. But it turns out if I tell you the bounds on the generators of the ideals and the function f, that's enough information to find your k. So that's enough information to find these regions where we've at least stopped growing for a while. So this is something we can get concrete numeric bounds out of, not good bounds, as I'll come back to a little later, but bounds. And relatedly, this is a statement we can take from the ultraproduct and pull it back down to those ground models. And so where we would have used noetherianity in this ultraproduct field, we could instead use this local noetherianity in any field, in the original fields that we started with. So in general, there's a language called L omega 1 omega. So L omega 1 omega extends first order logic by allowing countable quantifiers, countable conjunctions and disjunctions. And in practice, what's useful about that is it lets us just build into our language statements that involve the natural numbers and build statements about the natural numbers into our logic rather than into our language, into the language of first order logic. So you can say things like there exists a natural number, because you can think of that as an infinite conjunction of statements, or an infinite disjunction of statements, one for each natural number. So, theorem, if you have a statement in L omega 1 omega, there is this family of related statements, sigma AB. I'm not going to tell you the general translation because it gets a little complicated. I've given a couple examples. I'll give one more example later. But the relevant theorem is there is some family of statements so that if you know that that sigma was true in your ultraproduct, you get some kind of uniform truth in the original structure. So you get a statement of the form for every A, there's at least a bound B, so that in each of the original structures, one of these finitely many, or one of these boundedly many things holds. And this comes out of a line of work coming out of sort of investigation of non-standard analysis, going back to Palmgren about 20 years ago and through several other results. The underlying techniques are the same. The main difference is these are all sort of purely proof theoretic results that say if you have a proof in a given theory, you have an extraction of this kind. And I want to emphasize that this is a semantic claim. Like, I'm not making a claim about how you prove sigma. This is purely a semantic claim about how does truth in an ultraproduct relate to truth in the ground models. And the nice thing about this is this means for using this, we don't have to worry about what theory we're working in or what axioms we use in our proof. We really only need to know what did we get in the ultraproduct. So the important point is if you go through actual proofs that use ultraproducts, if you look at HTKM, if you look at Schmidt-Kirch, if you look at proofs in functional analysis and combinatorics that use ultraproducts, and you look at what are the statements of the lemmas, they're expressed in L omega 1 omega. So this is an adequate translation, and I want to emphasize I don't have any theoretical reason to think this should always be the case. This is an empirical claim that in practice, the things people use fall in this language, and so this translation is adequate. And strictly speaking, this is a false empirical claim. There are non-examples. In fact, Harrison Trainer, Claes and Musa goes through, well, actually stuff related to noetherianity that if you take it literally isn't formalizable in L omega 1 omega the way I've described it. What it's turned out so far is that every time someone uses something that isn't in this language, it's very easy to pull it down to L omega 1 omega. So it turns out people are using a special case or a corollary or something closely related, so you can pull the proof down into L omega 1 omega. So empirically what seems to be true is that what ultraproducts use are ultraproduct proofs use are the properties of ultraproducts that can be expressed in this language. But actual mathematics is not perfectly contained in this box, and there's some sort of work by hand to say, okay, this step goes on beyond L omega 1 omega, how can we pull it down into this framework? So one way to take that is to say this empirical claim is false. I prefer to take the rule that this really proves how strong the empirical claim is, that every time it looks like people are leaving L omega 1 omega, really they're working in L omega 1 omega, just phrased in a different way. All right. So the idea is this gives you a concrete strategy for taking proofs that use ultraproducts and turning them into standard proofs. And the idea is you just go through the proof and you take each lemma. And the lemmas, I've claimed, are going to be statements about in L omega 1 omega, so you can just translate them into standard statements, and then you prove each lemma. And if a lemma is hard to prove, that's got to be because the proof is complicated and long. So you break the proof into smaller steps, and you translate each of those smaller steps. And importantly, this is a feasible translation in the sense that this is a thing human beings can do in finite, achievable amounts of time. Relevantly, if we had to turn everything into sort of formal proofs in first-order logic, I mean, you may know that taking journal articles and turning them into fully rigorous proofs is an ordeal. I mean, it's doable, but what was it? The proof of the Kepler conjecture took something like a group of, several teams of people scattered around the world a decade to translate the proof of the Kepler conjecture into a computer checkable proof. Most journal articles are not as complicated as the proof of the Kepler conjecture, but if we had to sort of translate things fully into formal logic, that wouldn't be feasible. So it's relevant that we don't have to do that. What we just do is take lemmas that are short enough that we can use the original proof to guide us in identifying these lemmas, and then prove those lemmas by hand, looking back at the original proof for sort of guidance. And this is a not trivial, but an achievable process. These proofs are intrinsically constructive. I mean, these techniques come out of proof theoretic methods for taking non-constructive proofs and making them constructive. For example, so William Simmons and I took Harrison Trainer, Splice, and Musa. We unwound it into a constructive proof. We obtained bounds. The calculation of bounds, I think, maybe longer than their original paper. We get this function that we call g of omega to the m times 2 to the n. These are ordinals. G is actually the successor function in this context. So this is saying take a successor function and iterate it in a particular formal way, omega to the omega to the n times 2n times. This is not a small function. So omega to the omega would be basically the unary Ackermann function. Omega to the omega time, if you had a multiplication out here, omega to the omega times 5 would be the Ackermann function 5 times, more or less. So this is omega to the omega to the m. I don't have a good way of describing just how much worse than the Ackermann function this is, but this is a fast function. It's a big function by the standards of these things. So, okay, you get constructive bounds. You don't necessarily get good constructive bounds. There's no reason to think these are optimal bounds, right? This is actually, because these aren't giving new information. These are taking the original proof and giving you the bounds that were there. And if you write down a proof, there's no reason to think it's going to give you the best bounds or good bounds the first time you write it down. And in fact, maybe it's not surprising that exactly the proofs whose sort of underlying bounds are very large are going to more likely be done in these settings, and you're going to find that you get poor bounds. It does tell you where the bounds are coming from, right? It's not like giving you bad bounds for no reason. It's giving you bad bounds because the original proof had, poor bounds. So, for example, in HTKM, when we know exactly what goes wrong, the proof goes through finding a coherent autoreduced set. The construction of coherent autoreduced sets involves a long, if you strip it down to an ordinal induction, it's an ordinal induction of significant length. That's where, and you can go through the proof, and you've got perfectly reasonable, not great, but maybe exponential-ish bounds, right up until you hit that step, and then they explode. So this does tell you what would you need to do to get better bounds. You can look at their argument, and you can say, where are these bounds coming from? It's coming from this use of the coherent autoreduced set. The construction of the coherent autoreduced set involves, something like Dixon's lemma on sequences to prove that sequences are well-founded. In general, we know that Dixon's lemma has terrible bounds. I think as far as is known, for the specific cases of bad sequences of leading terms that come up in this construction, we don't know what the bounds are. Maybe there's a better construction of coherent auto-reduced sets, which would give you better bounds. Maybe you can give a different proof, which doesn't use coherent auto-reduced sets. But if you want better bounds, this does tell you exactly where the bounds are coming from, what you would need to do to make them better, which I think is sort of what you can reasonably hope for a method like this to give you. So William and I have been looking at the other proof I mentioned, Schmidt-Götsch, and so there's a paper on the archive, which, as some of you know, is incorrect. It's more or less right for the separable case, but there's a mistake in the inseparable argument, and we've been sort of bogged down trying to fix it. So right now we're at the stage where we exchange emails about once a week that alternate between, okay, now we know how to fix the gap, and oh no, there's still a little bit of a gap. But anyway, we will eventually have actual bounds for Schmidt-Götsch as well, using similar techniques. I have no idea what they are because we're still working out the proof, so we haven't actually sat down to extract any bounds from the argument. I have no idea what they'll look like. Okay, so if you can do this, why would you ever do it any other way? Why not just write down this argument directly? Why bother with ultraproducts? So one reason, and I think that unwinding of HTKM and that ugly bound there sort of suggests, one reason is that ultraproducts sort of compartmentalize a bunch of work with bounds and a bunch of work with sort of delicate calculations involving uniform bounds, and they just take care of a bunch of work for you. So you can focus on sort of abstract algebraic arguments and the ideas without getting bogged down in calculations. So I'll give one sort of quick example from Schmidt-Götsch's paper. Behind the screen, there. So it is. So a lot of the arguments in Schmidt-Götsch's paper involve the following idea, that you have this ring that I'll call K gamma of X, and it's contained in K int of X. So K int of X is this ultraproduct of the polynomial rings. So in particular, it has polynomials of sort of non-standard degree. Gamma, so for those who know these things, gamma is a cut in the non-standard numbers, and for those who don't, the relevant point is gamma is a way of saying in the non-standard numbers what it means to be polynomially bounded. And so really this is saying, here are the things that are whose degree is polynomially bounded, and here are the things that just have any degree. And then you do a lot of sort of either genuinely familiar or analogous to familiar arguments, where you do things like, well, this ring is flat over this ring, and you argue this the way you argue about flatness in general, and you just make sort of familiar algebraic arguments because these are just rings, and you can do the sorts of things you do normally when you have ring extensions. But they're hiding the fact that what's really going on is you're talking about taking things of unbounded degree and turning them into things of polynomially bounded degree. And it's just hiding all these calculations behind kind of more familiar algebraic machinery. So one of the things that ultraproducts really do for us is they do take things that are sort of involve a lot of calculations and hide the calculations and turn them into ordinary algebraic arguments. So that's one thing they do. The second thing they do, so I want to point out that these translations get more complicated. So I said I didn't want to actually, I said there is this general translation, I didn't want to write it down. So here's why. So it turns out as the complexity of this L omega 1 omega formula gets more complicated, as you have more exists for alls, the translation gets substantially more complicated. So here's an example. So the examples I know in algebra don't get more complicated than no theory entity, at least the ones I've looked at so far. So here's an example that ultimately came out of something in functional analysis, and somewhere actually sort of the key step in this proof about an example in Banach spaces. If you go through the argument, what is really going on, all the hard work is proving that that in a particular context, there's two limits that exchange. So the limit as n goes to infinity of the limit as p goes to infinity is equal to the limit as p goes to infinity of the limit as n goes to infinity of a particular sequence in a particular context. And if you unravel this into a statement in L omega 1 omega, one of the consequences, so because these were complicated, there was sort of some pre-processing trying to work with the simplest statements possible. You end up saying, one way to say that is, well, for every E is like a 1 over epsilon, right? For every E, for every N and P, there are an M and a Q, so that for every K and R, there are an L and M, so that AMS minus ALQ is less than epsilon. So this looks sort of messy. This is really like if you just, take calculus students who learn the epsilon delta definition of a limit. This is the epsilon delta definition of having a double limit. Like, this is nothing deep, but when you unravel it, it's kind of complicated. And when you apply this translation, you get this monstrosity. For every E, P, and N, and all functions K and R, there are an M and a Q, so that for all and functions L and S, and you get this thing. You can see the original structure of the bound. So the original structure said for every E, P, and N, there are M and Q, and notice M and Q, I don't know if the bold is coming across super clearly here, but M and Q are natural numbers. There are K and R, and notice K and R are functions, and we calculate the numbers K and R by applying the functions to the data. There exists L and S, and notice that to calculate L and S, we then get to apply the functions L and S to this K and R that we got. So that exchange of quantifiers for all exists becomes an ordering of how we apply functions. So the underlying sort of logical structure is still present here. We're going back and forth, but we have to go back and forth applying these sequences of functions. And then we get the same statement at the end. For the right values, they're close. This is not pretty. The same proof actually involves a statement that's one quantifier more, a pi 5 statement, which has another function that's sort of even more complicated. So these are the sorts of things that happen, and I think we can all agree this is sort of not a thing we want to work with regularly. Whereas exchanges of limits, like limits are familiar objects, proving that two limits commute is within sort of the ordinary scope of mathematics. So the Ultraproduct is doing a lot of work there, right? It's taking this sort of terrible, ugly statement about these interacting bounds, and what's going on is there's a complicated numeric dependency. Right, the L is depending on the K, which is depending on the M. It's taking this complicated dependency of values and turning them into more familiar statements that we can again do ordinary mathematics with. And the way I like to put this is, like, we in the end we kind of get the best of both worlds, which is to say, when we have these statements with complicated bounds, we can hide them. We can do these ultraproduct proofs. So what the ultraproduct proof is doing for us. And I mean, I want to make, especially for the model theorists, I want to make the strong claim that outside of model theory and set theory, where ultraproducts have other uses, every use of an ultraproduct in in ordinary mathematics is really what it's doing is taking some kind of statement about complicated uniform bounds and hiding the bounds and giving us a way to focus on sort of the qualitative information. And so we can get these qualitative conceptual ultraproduct proofs, and then we can translate them down into concrete, explicit constructive proofs. And we can go back and forth. So in sort of various special cases, I've been working for a while, including this work with William, taking known proofs in ultraproducts and saying, okay, how can we get bounds out? How can we give explicit proofs? And that's been productive, and I think that's interesting. I want to emphasize that I'm actually increasingly interested in going the other direction, which is to say sometimes you can find things in math where what you realize is people have hacked their way through messy bounds. Like, people have taken these arguments and done out the calculations, because these were the familiar techniques, and actually you can clarify things by going to the ultraproduct. And these complicated interacting bounds are really, like, when you see them, they're hallmarks in the literature saying, hey, I'm a thing that would simplify if you took me to the ultraproduct. So one thing I'm interested in is finding more examples where we have these sort of things that look like they come out of this, that have these complicated interacting bounds, where we could go and try an ultraproduct and see what we get when we do that.
How does this translation process differ from, let's say I take an algorithm and I do a complexity analysis?
Well, so I mean, we're starting with proofs that superficially don't have an algorithm, right? These are these sort of non-effective proofs. They're proofs on their face. They're proofs by contradiction. They say, suppose this doesn't exist, pass to an infinite counterexample and do abstract work there. So the work here is in sort of extracting the algorithm from that.
So any non-standard proof of any kind, you say you can get effective bounds of some kind. Is that what you're saying?
Effective bounds of some kind. And if it's if the proof is of a for all exist statement of that kind, then yeah, you should get effective bounds of exactly the kind you want.
So non-standard proofs of regularity lemma give what kind of bounds can you?
The non-standard proof of the regularity lemma is exactly the standard proof of the regularity lemma. Like it's the same argument.
We did non-standard proof of some stable regularity stuff.
Yeah.
And I'm not sure about bounds in that case.
Yeah.
Were there bounds coming out of?
Yeah.
Yeah.
Yeah. So actually, I mean, Caroline and I have been talking about that a little bit, and yeah, that is on my to-do list. Yeah, but absolutely, we'll have bounds.
Is there some, like, if you were just interested in going from proofs of statements that say existence of bounds to get existence of primitive recursive bounds,
Yeah.
but not actually extracting the construction that you did here, but just that there is some constructed bound. Is there some way, just from the form of the statements, without looking at the proofs, is there some way to absolute this?
So if you
the statement has a certain form, then as long as you prove there exists a bound, then in fact there exists a constructed bound.
So if you have a pi2 statement, a for all exist statement, and what exactly that means, how to make that precise technically is, you have to be careful, but it's a general theorem of proof theory that if you have a proof of a pi2 statement, then it's a constructive proof. And yeah, I mean, that's in some sense like Genson's theorem from the 30s in this special case, and everything since then is working out how to do that in practice and generalizing the setting to which it applies. If you want primitive recursive bounds, so you can't hope to have primitive recursive bounds from the syntax of the statement. What you could hope to do is say, for that you have to fundamentally say, you have to ask what are you proving it in. If you can prove something for primitive recursive bounds a kind of weak theory, then you're guaranteed that there are primitive recursive bounds. But as soon as you start using meaningful amounts of induction, you're suddenly you have no theoretical guarantees that you're going to get primitive recursive bounds. You really have to check by hand.
I have a follow-up to Rahim's question. So, in other words, this theory might produce like guidelines for mathematicians how to write your ultraproduct proofs that then they can be easily automatically turned into constructive bounds, right? So
yeah.
you have given a recipe. So if you do your proofs in this way, then you can claim that they result in a bound also.
Yeah.
Okay.
So as far as I understand it, the gamma you choose over there, it's kind of like a growth rate or something, right? Degree or something like that. Is that?
So gamma is a multiplicatively closed cut.
But it like bounds the degree of the non-standard elements that you're taking.
Right.
Somewhere.
Yeah.
So like, okay, I don't really know about this, but what kind of sensitivity can you have for that? Like, I think you mentioned polynomially bounded, but.
You mean like could you do other?
Yeah. Like
Yeah.
What kinds of?
So I should say, as far as I know, this is literally the only paper in the entire literature of mathematics that uses this technique. which I think is interesting because I think it's probably an underused technique, and I think this is an example of where one might want to take proofs that things are polynomial and say exactly. I want an abstract proof that they're polynomial bounds because I don't care about the degree. So that said, this technique is fairly general. So let's see. So if you wanted to say prove that something had exponential bounds of the form e to the cx, but you didn't care about c or something, you'd use a different gamma. So gamma has to have. So in this case, gamma has a certain property. It's closed under multiplication. You close gamma under something else. But in general, that idea that you can work with that different cuts express different kinds of bounds, or different families of bounds, that should be a general idea that I think has not really been explored.
Okay.